we have our host, Luka Jovanovic. He will be talking about reinforcement learning through gamification, learning how to learn with AI and video games. He's a master student at Singapore University, as I said. So everyone enjoy.
Thank you very much for the wonderful introduction. Here I am coming from the wonderful Singapore University. And today I will be talking to you a little bit about gamification, the theory behind how humans and AI learn through games. We will try and after that build a small game engine that will serve as an AI gym, where we can try and build a model that will slowly through an iterative process learn how to improve. We'll mostly leverage some very rudimentary and very simple algorithms here, just so it's still both beginner and intermediate friendly. So as reinforcement learning isn't a very, let's say, beginner friendly topic, usually researchers start with supervised learning, then slowly move on towards unsupervised learning through clustering, and very rarely is, let's say, learning through experience explored through this. So we'll actually have a very quick introduction on why this topic might be interesting, and then after that we'll start spinning up some code. So I hope everybody's received the supplementary material. There's a little bit of, well, there's quite a bit of Python code. Originally, I hoped to do the talk with a full coverage of, yes, we are having recording. This is actually being recorded right now. And as far as I know, we have the code already available at a link. We'll check with tech support for the specific link, but we do have the code uploaded everywhere, so you can follow along. And of course, this is being recorded. Thank you very much. So the first thing we're going to go is run through very briefly the ideas that we're going to explore here. So you'll just give me 1 second to try and share the exact screen. All right, so we should be able to see our screen here, and I'm covering everything on time. Well, I'm going to do this. And we should be able to see the presentation here, and I will be periodically looking at the Q&A. So, reinforcement learning. We've seen it, and it's become all of the rage in recent years, mostly because supervised learning usually revolves around I'm going to have a check with tech support, but we are going to have it linked in chat in no time. Now, there we go. We have it in the chat, which is the Jupyter notebook, and you can follow along with that. Also, we're going to be implementing most of that here live as well. So, as I've said, reinforcement learning has in recent times become more popular than years before. There's several reasons to it, mainly because we have more computational power available. So 10, 15 years ago, CPUs were the workhorse of the, let's say, machine learning engineer. Nowadays, we have specialized GPUs, and we even have TensorFlow processing units. The code should be in the chat right now. So there's a Jupyter notebook with the download in the chat. It's just a IPYNB file. You can run it either in Google Colab, or you can use Jupyter if you have it set up. Somehow copy this from. In any case, we'll be uploading everything. You should be able to go into more and then open up chat from there and be able to access it without a problem. I'm not sure I can actually upload the files here. Chat is disabled. Give me just 2 seconds here, and I will reshare the screen for that. So give me 2 seconds to upload the files into the answers. Not sure if I can actually upload files through the . Let's see if we can upload the code directly. Directly to the feedback here. Fortunately, no. If I can just ask tech support to re-upload it to a chat where the participants can also see it. I'm having some trouble with direct upload here. In any case, we'll start with the presentation and then hopefully tech support will, by the end of it, have us covered as far as the upload goes. If not, we'll resort to using either GitLab or Dropbox or something similar. So let's firstly talk about, let's firstly start talking about the theory behind what we're going to do today, and then we can start with the implementation, and I'll make sure that we have everything set up before that. So, like I said, reinforcement learning has recently become more and more popular among AI engineers and many other, let's say, researchers in the field. Where supervised learning takes a lot of expertise, reinforcement learning lets us kind of avoid having to have an expert on the topic. Another kind of difficulty here is that if you're even an expert on a specific topic, there doesn't necessarily need to be a direct way of getting to that point. There could be a few steps there that are difficult to attain. So if you consider it, for instance, the chat model, you can be a linguist and still very much struggle with determining what is a good conversation. Is that conversation rational or not? So that's where we kind of leverage reinforcement learning here. We look at samples, we let them loose in an environment, and that environment provides the feedback to the specific model. So if you consider, for instance, the chat model, you let it interact with users, and those models that perform better, you kind of keep, and then you improve on the formula. It does require a little bit of brute forcing, so there's no direct procedures to kind of see the process going forward. It requires a little bit of feedback from the environment forward and back. And we'll see how we can leverage some objective metrics to do that and how we can kind of improvise depending on the specific problem. So what is gamification? This has become a popular topic in psychology, and as many things AI related that stem from the field of psychology, gamification has kind of crept its way into artificial intelligence as well. Gamification is the idea of converting some kind of a task or everyday task, any task at all, into a sort of game with smaller tasks giving a little bit of a reward. So this is quite popular with people who are trying to, for instance, learn a language where they would convert a few steps into a game. There are popular applications that convert, for instance, having 1 lesson, 10 lessons, 100 lessons as a motivator for staying focused on the specific language that you're learning. And this has several, let's say, steps. Usually people try to address a very daunting task head on without kind of considering the amount of work and theory that's going to be needed for this. So for instance, if you wanted to tackle learning a new language, there's quite a lot that you need to do head on. You need to memorize a lot of words, you need to memorize their meanings, you have to memorize the grammar, and depending on the specific language, pretty much with any language, it's going to take a few years at best. People tend to get demotivated when things take too long. And this is mirrored in AI algorithms as well. If you have a neural network training on something and you can only grade it once it's completely done with what it's trying to do, that's not a very good algorithm. It's not going to be very, it's not going to be very efficient. It's eventually maybe going to stumble on what it's supposed to do, but realistically, it's going to struggle a lot. So we leverage a few psychological principles in reinforcement learning in order to motivate our algorithms to learn a little bit better. So there's a few specific techniques on how to do it, but in our case here, we are going to look at a specific, let's say, scenario. So it's an effective tool for education. It's also an effective tool for training. So why not try and implement it in artificial intelligence as well? So we can create an immersive environment, and this facilitates learning through simulation. So in some countries, driving schools for new students have implemented, for instance, driving simulations where you can sit and practice driving before actually risking a vehicle. A lot of driving schools which focus on professional drivers, for instance, have complete simulators where you can sit and drive before you're actually on the track. And the idea behind this is that it's much cheaper. And again, if we go into more complex examples of this, we also have we also have simulators for planes. A lot of flight schools, for instance, don't let students just focus on theory. They let them experience some of the, let's say, problems that they might run into through a safe simulation. And this is something we often leverage in reinforcement learning. So instead of crashing 100 vehicles to try and teach an algorithm to park, we can make a simulation of a parking, let's say, parking minigame, where we enforce an algorithm trying to park. This way, we can crash 100 simulated vehicles with zero to almost no costs, which then allows us to train an algorithm that can then be tested in the real world. Now, why do humans play games? As of not so recent studies, not only humans play games, a lot of animals, mammals, so forth, also engage in games. Well, this allows, let's say, young individuals to experience some of the hardships of life and complex tasks in a simple and fun way. While games can kind of be seen as a waste of time to some, it is also a very valuable learning tool. So through experience and simulations, we kind of learn how to apply these skills to other more complex tasks. Games also often present very challenging tasks with smaller goals. So they also teach individuals how to break a complex task into a series of smaller tasks that can be strung together to accomplish something meaningful. And they also provide a sense of accomplishment. And it's this sense of accomplishment that we mostly leverage in AI. So this is going to be our reward for our algorithm. Our algorithm is going to be given a relatively simple or relatively complex task. And then through a series of small improvements, eventually our algorithm is going to learn to solve a fairly complex task. And another thing that's kind of offered by, let's say, simulations is that they often require strategic thinking. It's not always a, oh, well, this is what you do, and these are your results. Even so, doing something like that usually isn't rewarding for individuals. So you can cheat in the game and still achieve reasonable success, but dopamine kind of dictates that you're going to have to force your way through it. It's the difficulty that makes it interesting. And finally, playing can also improve cognitive abilities. This can improve reflexes, develop various skills depending on the nature of the specific game. Many institutions have leveraged a sort of video game format to improve learning and training. So finally, as I kind of mentioned, we want to talk about learning from games in a safe way. So certain skills are kind of difficult to develop for cheap or for free. So if you, for instance, consider driving, it takes a few years to, or rather it takes a few months or weeks to kind of learn the theory behind driving. Then once you're behind the wheel, you need to have a little bit of experience to be good at what you're doing. So it's kind of a catch-22. If you need experience in order to be good, you need to be good to get experience. And if we're talking about vehicles and other topics, I'll make sure to ask technical support once again, if you can please post the files in the chat so we can kind of code along once we're done with the presentation here. So as I've said, if you think about more complex tasks, such as flying a plane or driving a car, this becomes exponentially more difficult when doing simulations. So you can't really afford your algorithm crash a few planes in order to learn how to fly. What you do is you create a soft simulation. You kind of go through a handful of steps and incrementally teach your algorithm in a safe way. This is very much how humans work. When we play games such as tag or similar simulations, there is not a serious punishment for kind of losing, but it still teaches you a valuable lesson. And of course, winning feels good. So games provide us with instant feedback on our actions. And this pretty much very quickly lets us kind of learn from what we've done. And again, having a game that doesn't have serious consequences allow us to do this in a very safe way. So games are, let's say, a little bit of theory behind what video games are. So in physics, we usually rely on hard simulations. We would create some kind of an experiment, carry that experiment out, see what the results are. Games are kind of an interpretation of this in a, let's say, computational way. There are two kinds of sorts of simulations that can be done on a computer. We can do a hard simulation where everything needs to come, basically happen instantaneously, or we can have a soft simulation where some things can be a little bit delayed and not 100% realistic. However, games do allow us to create immersive real-world environments where we can simulate real-world scenarios and provide a platform for users to experience both the negative and positive scenarios in a virtual way without any kind of consequence. And of course, soft simulations in games provide us with a safe space for users to learn from failures and mistakes. This makes it very usable for individuals trying to learn, let's say, a complex task that can be very expensive. And finally, the consequences that carry from games are usually negligible. We will feel a little bad, but nobody will be hurt while we're learning to do something in a game. Let me just check with technical support here. Sending the file to chat. Once again, I'll try and send the file to chat as soon as we're done with the presentation, and before we start coding anything, we will try and see the material presented for everybody. So let's look at how reinforcement works on a real-world example. Let's say you're trying to teach your pet a trick. Well, your pet can be considered an agent inside of a simulation, and you throwing that stick becomes the environment. So if you're, for instance, trying to teach a dog to play fetch, you would throw a stick, and then your dog would kind of run after it, and come back. Not great, not terrible, but not the entire process you want to have your dog do. You want to go throw your stick, the dog runs to the stick, grabs the stick, brings it to you, lets it on the ground, and then you repeat the whole process, where you would consider this to be a successful training session. Well, it usually doesn't go like that. Very rarely do individuals, animals, agents perform the action first time well. It usually takes a lot of time before they kind of click with the entire process. So the idea here is to kind of reward specific actions. So how would we do this? Well, if we look at the, let's say, training a dog to fetch, first we would, get our dog to get excited to go outside and show him the stick, let him sniff the stick, and so forth. The next step is teaching our dog to run towards the stick. Now, instinct kind of helps us out here. The dog will most likely intuitively go after the stick. So the first few times we're going to throw the stick, then we're going to walk up to the stick, give the dog a little bit of a treat, and the dog will learn that running after a stick equals a reward. We've already established one kind of step here. The next step is trying this over and over and over again until one time the dog kind of forgets that he's just supposed to sniff the stick and comes back with the stick carried in his mouth. At that point, we introduce another reward. So we would reward him a little bit more if he brings the stick back. Of course, dogs being dogs, they're probably not going to give up the stick easily. It's going to be kind of a push and shove until we've kind of gotten to a solution here. But ultimately, we have a third step here. We want the dog to be able to fetch the stick, bring it back to us, and to let it go. So we would slowly phase out the reward for running and sniffing the stick. That is a kind of established behavior. We would only reward behaviors for bringing back the stick to us. Now we would do the same thing. Eventually, we would tease the dog with a little bit of a treat. They would kind of drop the stick. We give them a bigger reward. We repeat this until the entire process is successfully enforced. And this leads us to a complete, let's say, training session. The next step is slowly phasing out the reward. So what psychologists have kind of established a few years back, that constant reward isn't always an effective method. After the behavior has been established, only occasional reward provides the effective feedback. So if we reward our dog every time, eventually they will no longer be motivated by treats. So what we do is, once we have that behavior established, we slowly phase out treats. Maybe we provide a treat every other time. Maybe we provide a treat every third time, and so forth, until we phase that behavior, or rather the expectation of a treat, completely out. This does two things. Firstly, we have a dog that now knows how to fetch. And secondly, this dog is not, let's say, immune to our reward. We can teach it to do something else. Maybe we want to teach a dog to roll over. Now it knows, okay, different action, different procedure, different thing, different reward. So this is the kind of complete outlook into how reinforcement learning works in real life on a semi-intuitive example. So if anybody's ever seen a dog or trained a dog, they very quickly learn how reinforcement learning works. Another thing to kind of mention about this is that there's two types of reinforcement. The first type of reinforcement is teaching the dog, or rather a positive reinforcement. We reward good behaviors, and the second one is negative reinforcement. So this is when the dog does something we don't like, we would provide punishment. Now, in practice and biological animals and everything else, this really doesn't work. But in our simulations, we can do that. So we can decrease some points if something is done completely wrong. So for instance, we throw the stick in a direction, the dog runs away from the stick, we would then not provide the treat for the dog, which would not reinforce this negative behavior. Well, all right, that works fine. But as anybody who has had a young dog knows, they'll very quickly get bored of this one task. They will put their little paws down, lay down, and be like, oh, I'm not hungry anymore. This is not worth it. So let's move on how we can actually make agents do this in a simulated environment. So we can look at our agent, or originally our dog, as a robot looking at a screen of some kind of an environment. Now, this can be a real world environment. People have trained drones to fly using reinforcement learning. So they would create a cluster of drones, have them fly around and train. Alternatively, you can create a simulated environment, which cuts your cost down significantly. So you can create a relatively simple video game. You can create an agent inside of that video game that's represented by a player, and then have that agent play a video game. The agent would perform some kind of an action, and based on the results of that action, the environment will provide a reward for our agent. So think of this exactly as you would think of the treat for a dog. If our Pac-Man, for instance, simulation, manages to run away from a ghost, we will reward it. If it doesn't, I'm sorry, we will withhold the reward. And finally, based on the observations, action, and rewards, our agents will progressively get better at what they're doing. The amazing part about this, as far as computation goes, is we can do this indefinitely. So agents will not get tired. Practically, we can do it forever until we get an agent that's ready to do it. If we were to do this in a real-life environment, we would have a few attempts. And having an agent that's pre-trained on an approximate simulation gives us a very good system for applying it in real life. All right, so let's say we've kind of slapped together our agent, but all video games have agents. That's the player. Let's think about how we play the video game. If we look at any video game ever, the first thing we have to do is kind of look at the screen. Let's see what's going on. Then we need to kind of process what's going on and then determine what's the next step we're going to do. The way we do this with our amazing, huge brains is we have interconnected neurons, a very complex system of electrochemical signals, and a lifetime of experience to do something. Agents in video games and simulations and so forth are not this powerful. Even the best supercomputers in the world can only simulate about 5 or 6% of an ant's brain, so we're not going to be doing a complete simulation. But what we can do is we can simulate a part of it. And this is where we go into the topic of artificial neural networks. So everybody here, I hope, has heard of artificial neural networks. They are all the rage. A very flexible artificial intelligence algorithm, again, coming to us from the field of psychology all the way back in the 50s and 60s. The idea behind artificial neural networks is that there is a specific input layer in our simulation of a net. This network has interconnected neurons, and each one of these neurons has a specific weight assigned to it. We have 3 major types of layers, and then we can kind of combine what we're doing specifically. But the first layer we kind of encounter in our network is the input layer. Inside of the input layer, some experiences from our environment get converted into numbers. How this is done is largely irrelevant and depends on the specific simulation, but the experience of our environment gets converted into numbers. These numbers are then processed through subsequent layers. So each one of these not first order layers, so these hidden layers, acts as a processing node. The neurons from the input layer are then interconnected with subsequent hidden layers where some kind of aggregation is happening. So whether this aggregation function is a sum function, multiplication function, dot product function, really depends on the specific implementation, but all of the inputs are somehow aggregated together and run through an activation function, usually a sigmoid function. Now this sounds kind of complex because we use a lot of mathematical jargon, but what that just means is that a certain number is calculated based on the inputs, and that number is converted to a value between -1 or 1, or depending on the specific function, 0 to 1. So we kind of look at a bunch of numbers and then convert that into one number. And then we do that a whole bunch of times. And finally, when we have that processed, we provide that to the output layer. The output layer then determines, again, the value of an activation function and provides that with a number. So we would, for instance, show the entire screen to our algorithm and then ask that algorithm, well, should our agent jump or not? Is it close to a bridge? Is it close to a platform or something else? What is the next action our agent is supposed to do? And hopefully through experience, our algorithm will have kind of seen similar scenarios and would be able to kind of interpolate that, okay, this is the point where we're supposed to perform an action. So we could assign a simplified version of a neural network to each one of our agents. This allows us to build intelligent agents. So our agents can react to the environment, and more importantly, our agents can update what they're supposed to do in that environment. So usually how artificial intelligence is handled in video games is we have strict if-else statements. If something happens, you respond like this. If something else happens, you respond like this. If you're close to an edge, turn around and walk back. Pretty good. It's proven effective to be somewhat fun. But as the player gets better in these things, agents are going to become predictable. So what we can do here is we can make an agent that learns from what is going on. So our agent experiences the environment, learns from that environment, and most importantly, adapts. So as an agent plays the game, it actually gets better to it, at it similarly to how a player does. So that solves the problem of our agent. We have an agent that can look at the environment and kind of, by adjusting weights and biases in the neural network, get better at navigating that environment. There's a few other things that we're gonna have to address when we start implementing this, is that similarly to real-world problems with overfitting, our agent can memorize the environment 100% and simply not have to react to it. It will memorize the order of the operations and be overfit to it. So we need to kind of randomize our environment a little bit. But the second part here is, again, of this reinforcement learning gym that we're going to be looking at here is reinforcement learning, or rather is the environment we need to simulate. So we've talked about games as simulations. And here we can look at a very simple example that we're going to be building here. So what's the difficult part of looking at a specific problem or environment is what information does an agent actually need. So if we look at an example of a crude neural network, let's say we have a network that can predict whether it's going to rain tomorrow or not from an image of the sky. So I provide that network with an image. It looks at the image and kind of interprets that data and says, okay, we're going to be seeing rain tomorrow or not. What's going to happen if I show that network an image of the floor? Well, the network is not going to be very certain. So it's very important to have proper inputs for an agent that's going to give us mostly proper outputs. Kind of a push and pull scenario here. But what we're trying to accomplish here is that we need to provide proper information for the agent to be able to learn. So if we give our network irrelevant information to a specific problem, we're going to get poor advice and poor decisions on that from that agent. And this is a well-known concept in machine learning, often referred to as garbage in, garbage out. If you give your network too much information, it's not going to be able to adapt. If you give the network irrelevant information, it's going to not be able to adapt. And in our simulation, we're mostly going to be looking at a few simple values here, simply to keep the, let's say, time we needed to code this to a reasonable amount. But the process carries over everywhere else. So we're going to be looking at a simulation of a relatively well-known video game from about 5 or 6 years ago that was very popular for the Android platform. It's called Flappy Bird. The basic idea is that the user flies a little bird. Every time they tap the screen, the bird slowly jumps. The idea of the game is to avoid obstacles and kind of go through these simulated little pipes. Very simple, but exotically challenging. I've spent many a days trying to beat it on the phone and have yet to beat a reasonable score. Again, individuals have gained hundreds of thousands of points, but the game is essentially endless. And for humans to do this, it usually takes a couple of months to kind of get to it. You kind of learn the timing, you observe the screen, and you kind of get good at it. We're very strong learners, even in our older age, so we can adapt to these problems. Doing this with the network is slightly more challenging. We need to provide the network with individual information, and these are kind of the parameters that we're going to be working with. So the most relevant value that we need to look at is where this gap is in relation to our bird. And that's one of the parameters we're going to provide. Second one is what's the distance between our bird and the specific pipe. It needs to know when it needs to time its jump. We need to know the velocity of this specific bird. So the velocity can be positive and negative, and it's going to slowly jump. This information lets the agent know when they should time their jump. And finally, we need to know the height of the bird. So we can see that the correlation between the height of the bird and the height gap here is the value that we're aiming for. So we want to kind of balance those two so the bird can make it through this gap and not hit the pipe, which would constitute the game over. And we also need to have the pipe distance and bird velocity here. So these three values let us make an informed decision. And these are the values that we're going to be providing to our agent, simply because it boils it down to 4 inputs. So let's talk about how agents are going to get better. Well, we're going to take something called a population-based approach. There's several ways on how this is done. One is, of course, letting your agent into the environment and hoping for the best. That's all right. But what a population-based approach lets us do is that we can generate a population of agents that are somewhat similar, somewhat different, kind of randomized. And then we can run this population of agents through our simulation. And then after the simulation is done, based on their performance, and we'll look at objective functions in a little bit more detail as we start implementing them, we can then reward well-performing agents. In our simulations, we're going to be leveraging a principle observed in evolution. So we're going to be creating a population of about 100 individuals, running those individuals through our simulation, and then we're going to be selecting the best individuals from there. The best individuals we have are going to remain in the population, so they're going to survive an iteration or an episode, as it's called in reinforcement learning. They're also going to produce children, so we're going to take some of the best agents, we're going to recombine some of their traits, and create agents that kind of inherit the best from both agents. This is how we simulate natural selection in our algorithm. And finally, we're going to perform selection towards a more optimized population. So agents that perform poorly are slowly going to get phased out of the population. Agents that perform well are going to be more established. They're going to have more children, they're going to have more agents, and these agents themselves are going to be having more offspring. But one challenge here is, how do we encode genetic characteristics for a specific agent? So our agent is simply a group of neurons inside of a neural network. How do we encode this? Well, this brings us to the genetic algorithm. So we've heard about the genetic algorithm. It's a very powerful optimizer, but it's kind of not utilized as much as it could be. It's amazing for reinforcement learning because it simply lets us recombine data together to provide a data-driven approach for agent improvement. In our case of genetic encoding, each one of the weights can be considered a specific gene. So if we look at a neural network, it's mostly characterized by two things. It's characterized by the number of layers. However, since our agents are going to be all the same, we can just assume that the number of layers is going to remain consistent. It's then characterized by the weights between each one of the neurons. And finally, it's characterized by the biases. Now, the role of biases is to remove the possibility of a specific value becoming 0 and then becoming ignored in our calculation. We're going to kind of remove the variable of biases within this. It's going to give us a slightly less good, well-performing algorithm, but it's still going to translate the idea fairly well beyond this. And the second part is the weights. So the weights are the characters, or rather the main driving force between how these calculations are going to be handled. So for each one of the weights we have in our neural network, we're going to create a genome that represents those weights. Once we create that genome, that's basically weights in layer 1, weights in layer 2, weights in layer 3, we're going to leverage the genetic algorithm to do two things. Firstly, we're going to kind of create offspring from these algorithms. So we're going to do a little bit of cross encoding for the genes. And finally, we're going to do a little bit of mutation. So if we rely too much on creating offspring, we're going to run towards something called early compurgation. Our algorithms are going to converge towards a suboptimal space based on the experience of their parents. So unless a random agent shows up that's suddenly the best agent ever, there's a very low chance of algorithms passing through the next generation or making a breakthrough. So what we're going to be doing here is we're also going to be mutating existing agents. So the next thing is the genetic crossover idea here. It's fairly simple. This is how humans mostly do it. We have a parent's genome, which is then recombined to have a child's genome. So from each parent, we would create a new child that represents a combination of their genes. In our case, we're going to be doing this with a little bit of randomness. There is some rules in nature how this is done, but in our case, we're going to select two random best performing agents, and then we're going to recombine their genes to hopefully get a better performing agent. The second part here is genetic mutations. Now, in nature and in most genomes, genetic mutations occur semi-randomly. So we go through the genome, and sometimes errors in copying, errors in combination will create an odd behavior. So we will have a genome that just isn't it. Usually this results in horrible things, but occasionally this will fluke and create a improvement. And mutation is very important in the genetic algorithm because once we have an established population, this helps us introduce new agents that are slightly different from the norm, but still perform fairly well. And finally, we're going to talk about how does this manifest in a reward system. So our goal here is to, once we start our simulation, be able to select agents that are going to produce the best possible result. This is fairly simple. We evaluate the fitness of each agent. And in our simulation, it's going to basically be looking at agents and how long they can live for. So we're going to run these agents through the simulation. For each step that we take with our agent, we're going to extend its fitness value by 1. So if our agent survives for a minute, it's going to have something about 60 times 60, about 1,200 points. It's not going to live that long in our environment. The game is fairly tough. But the longer an agent stays alive, the higher chances that it's going to have offspring that are. The second part is, once we've done with our simulation, no agents in our population essentially survive, we're going to perform crossover and mutations. We're going to create a population of children of the best performing agents, and then we're going to mutate some of the best agents to create a smaller subpopulation of mutants. And through an iterative process, so while we carry out each and every one of these simulations, we're slowly going to select towards optimized agents in our gym. And finally, since we've kind of run through the ideas here, we want to look at the code. So we're going to focus on Python code here. And like I said, theories are like parachutes. They work best when they're open and put into practice. So let's see our example here. I'm going to stop sharing for a few seconds and then try and share the code through the Q&A. 1 second for the upload. For now. You can have to send the file. All right, there should be a, no, that's the PPT. And that should be our code. All right, can somebody just confirm that they can see the files in the chat? We have them on the drive. Awesome, awesome. Thank you very much for the tech support. So we can start looking at our example. So now that we all have our code, let me just share the screen once again. And hopefully this all carries over well. Thank you very much for the feedback. So let me just share my screen once again. All right, and here we have our code. So originally I was hoping that we would do this live coding, but technical constraints and mostly time constraints slightly limit what we can do here. So we're going to very quickly run through what we have presented in the code, and then we'll start looking at simulations step by step. is the screen shared? Can you see it now? Right. This should be a little bit better. I think that's about the maximum that we're going to see. Is this code fairly visible? Thank you very much for the feedback. So, as I've said, originally I hoped this would be a kind of live coding thing, but I very quickly realized that there's a lot of code to kind of type on the spot. So we're going to run through an implementation that I've done, and then we'll kind of focus on the parts that are the most important. So initially, there's two things that we kind of need to do. Since it would be very much out of scope to start and run a rendering system and a timing system and everything else in just one session, we're going to rely on a little bit of libraries. So we're going to be using Pygame, which is a open source and fairly popular library for building engines. It is mostly a framework, but it's very moldable as far as users go because it's very user friendly and comes with a lot of examples. The second part, which can be a little bit tricky, is the specific version of NumPy. So the reason for this specific version is because we're doing a little bit of trickery with NumPy for a specific conversion that has kind of been replaced in 1.14. So we can't really do it with the newer version, but there is a small correction in the code which will allow it to run correctly. Let me just check here. All right. So there is a small correction that can be done to make this work with even newer versions of Python. Double check if everything is working here. All right. So the first thing we're going to do here is import a handful of support libraries. So we're going to need our Pygame, we're going to need our system library. The system library is mostly used to be able to exit our system, or rather to exit our code without causing a terrible crash. We're going to need the random library. Can tech support just to confirm that they can see and hear me? I think my camera might have frozen. Try to keep. All right, there it is. So we're going to import Pygame, our system, our random, and our NumPy. And these are the building blocks in our code. So those of you that haven't experienced Python yet, this is how you can fetch external libraries. The second topic we're going to look at here is we're going to be using something called an entity component system. So the entity component system is a template for building applications. It's mostly popular in video games. And a lot of more complex video games rely on entity component systems. So if you look at older roguelikes that have more complex systems, such as Alchemy or Rogue or Dungeon Crawl Stone Soup, they would usually leverage an entity component system mostly because there is a lot of systems that need to work together. It has a little bit of boilerplate that needed to write it, but a kind of side effect of once this boilerplate is well written is that we can then reuse it in different scenarios. So I've made one simple here, which simulates the Flappy Bird video game, but this code can very easily be adapted to any other kind of simulation. So either a top-down RPG where a player learns to navigate some kind of a maze, or a driving game, it's fairly flexible. But we do need to implement a few things that are needed for this to work. So the first thing we're going to be looking at is writing an entity. Now, the entity component architecture or template, it's very much data-based. Another reason why I've selected for this, let's say, tutorial is because of its kind of flexibility of data flow. It's also very well merged with functional programming. So the first building block of an entity component system is the entity itself. And an entity is an abstraction. An entity can be anything else. If you remember databases or any other point, an entity is just something that contains data. So essentially, you can think of an entity as a bag of data where we can put specific values. And the way the entity is implemented here is as a relatively simple vector. The only thing that kind of needs to be paid attention to is that each entity has a unique ID. This lets us track it back through data. One advantage of this architecture is that it's very memory efficient. It's not very memory efficient in Python, but once implemented in C and C++, this lets us work through memory way faster than any other implementation. So again, one tiny little limitation of the Python interpreter is the way it kind of treats memory. It's not the most efficient way of doing it, but the philosophy of the entity component system can be translated directly for any other, let's say, system or programming language. So what we have here initially is the entity itself. So the first thing it needs an ID. So what it does is it increments its internal ID so we can identify it later, and it initializes a little empty dictionary here for its individual components. Now, components are the values that let us describe the entity. This can be the entity's location, the entity's current health status, the any information about a specific entity inside of a simulation is going to be contained as a component. And components themselves are very simple. They're just going to consist of a name and a value. A name lets us retrieve this component very easily from an entity in an intuitive way, and the value lets us work with this specific value. So if we store a value for HP, we can access it through entity.hp, and this will let us work with it in a specific system. We basically need two, let's say, ways of working with this. We need to be able to add a component, and we need to be able to remove a component, and this is done in a similar way to vector implementation as well. We then have neural networks and a little bit of crossover. We're going to skip that for now, and we're going to talk about systems. So any video game ever needs to have a couple of things happen simultaneously. It needs to have a user system, which is how the game gets feedback from the user. And in our case, we only have a handful of events that we're going to work here. So we have our user system that creates a new pack of endpoints. Why do I do this? Well, this is kind of a leftover of functional programming. It makes mistakes much easier to catch. What we do is we provide our user system with a batch of entities. These are all the entities we have in our game world. And our user system does all the transformations it needs on this group of entities. But it does not change them in their raw value. We try to keep immutability in this example. It creates a new array of entities that's then going to be kind of altered. So what we do here is the first thing we want to do is store our events. So an event is kind of a parallel system that's going to be running along the Pygame where they're going to be storing keyboard and mouse events. In our case, we only have the keyboard event, which is going to simulate a jump. And it's going to run through an event system and check for two things. First, it's going to check if we have a press for an escape. This is going to close our window in case something goes wrong. And secondly, we need to check if we have a press the space bar. What the space bar does is it's going to make an engine kind of slightly jump. And finally, we want to alter the specific jump component. So our entities that are going to represent players are going to have a component called jump. Once this component jump flips its value to a 1, the agent will perform a jump in the video game. And this basically heals our user input system. So our game can interact with the outside value, or rather with an interaction. The second part, which can be a little bit daunting here, is the rendering system. The rendering system simply displays our game to us so we can visually see what's happening. And in our system, we only have 3 or 4 components. We have a few birds, and we have pipes and the background. And the first thing here that we're going to do is we're going to open up the screen. We're going to initialize Pygame, which lets us work with some of the backend API calls. We're going to set the caption on the screen. Then we're going to draw our agent. So we're going to check if this agent is itself a bird. We're going to do that by checking if it has a bird X value and if that agent is alive. We'll talk about what constitutes a living agent or not in a few examples in a few minutes, but we're going to check if that agent is alive. And the second thing that we're going to do is draw that agent. Now, we have another component here we're going to look at in a more intuitive way once we actually start running the simulation here, but I will also keep track of this agent. So if the agent gets randomly generated, we're going to paint that agent yellow. If that agent comes from a previous generation, its best performing agent, we're going to paint it red. If the agent is a child agent, so a combination of 2 of the best performing agents, we're going to color that agent green. And finally, if our agent is a mutant, we're going to color it blue. This lets us track our algorithm's performance through the optimization process. So we don't necessarily need to keep super detailed logs. We can just look at the algorithm and know, okay, our child agents are performing well. Our senior agents are performing, of course, as expected. And we're seeing the best improvements of our mutant agents. So this lets us kind of get an intuitive feedback on what's going on as far as this goes. And finally, when we do all the rendering, second part, after birds, we're going to draw the pipes. Pipes are fairly simple rectangles that move across the screen. An example of that, nothing too difficult with that. Another segment of this is the physics system. So what the physics system does is it applies changes to the world based on a set of rules. We really have only two rules. We move agent downwards if their velocity is negative. We move agent upwards if their velocity is positive. Or we move agent downwards if their velocity is positive, upwards if their velocity is negative. That helps us kind of keep a gravity, gives us a little bit of difficulty to the game. And the second thing here is we have our pipes that move sideways. These represent our obstacles. The physics system is fairly simple, but it's an integral part of the second segment here is our collision system. So what the collision system does is it checks for collisions of agents with pipes. The way it does this is once an agent is within range of a pipe, it's going to either flag the agent as colliding with that specific pipe, or it's going to say that it has not yet collided. And how this collision is going to work is once a bird hits a specific pipe or any pipe at all, its status is going to change. So a bird that hits a pipe is not going to be considered a living agent. And finally, we have our jump system here. The jump system is 100% dead simple. If a bird has a jump value, it is going to jump. If not, or rather its velocity is going to be flipped, which is going to cause the bird to jump. And if that value isn't, it's not going to jump. This kind of plays back onto the neural network that we're going to be looking at next. And secondly, we have our reward system. So what the reward system does is, we've again noticed this, is that the longer the bird is alive in our simulation, the reward it's going to have. So if the bird goes through the simulation for 1 minute, maybe hit it, or other goes to the first few seconds and then immediately hits a pipe, it's not going to do very well. But if the bird makes it through a few of these pipes, our simulation or our game is going to reward that agent a little bit more. And finally, what comes after that is the AI. So we're going to come back to the AI system once we look at the networks. The next segment is the reset system. So once no agents are alive, we are going to reset our simulation. That lets us very quickly run through quite a few population simulations. Another thing that we're going to come back after we talk about the neural network and the crossover mechanisms. And finally, we have our time system. So this time system is very important in recent times. Back in the ye olde days when Commodores were king, games were written in such a way that they would run as fast as your processor can simulate them. And this makes it very difficult for humans to track games. You can't simply compete with a game that runs at as much as a modern CPU can do this. The second issue with this is, of course, consistency. So if you're running it on 3 or 4 computers, you want your game to be repeated. You want it to run the same on a computer from the 2000s to something on a 99 or something like that. So you want to have these things run consistently. And this is where this frame rate tick goes. So what happens is that our game is going to try its best to maintain a consistent frame rate. And to do the simulation, then it's going to wait a small period of time, hopefully wait for a small period of time to repeat the whole cycle once again. The point of this, of course, being that our simulation won't get out of hand. It won't happen too quickly for us to track. And finally, this is what the game looks like in a entity component system simulation. We just call a function that calls all our systems on all our entities at all times. There is nothing else that happens in an entity component system. We define our systems, we define our entities, and we apply those systems to entities in an indefinite loop. Very simple, very intuitive, with, of course, a little bit of work for sectioning the data off. But as we can see, it's very easy to implement and understand in a semi-intuitive way. So the next step here is when we actually want to run our game, we need to define our entities. And the system basically follows a handful of rules. The one thing that's kind of different here is that we're going to be using a population of agents. So in an ideal video game, you would have one, maybe 4 players, and those players would do their simulations fairly straightforward, one step after the other. We would be done with our simulation. However, if we want to train an algorithm, perhaps this isn't the best idea. So let's look at how we could do this. We could run this simulation individually for each agent one by one by one. That means that for a population of 100 agents, we need to play 100 games to get the same results. So why not flip it on its head? Why not simulate 100 agents in a single game and just select the best ones from there? So this is the population-based approach that I've talked in the previous example. We're going to simulate a group of agents and then only need to run one simulation for all of these agents. If we were, for instance, learning how to, or rather teaching an algorithm how to park a car, why just give one car to the agent? Here, make 100 agents and park 100 cars. Those that park correctly make it through the next generation. Of course, the simulation costs kind of compound here. So if you have more complex agents, it's going to be a little bit difficult to run a 100 agent population. But in our case, since we're going to be using a fairly straightforward, just a feed-forward neural network with no backpropagation or anything similar, we can simulate a fairly large, in our case, 100 individual population, and we'll see how we can do this even bigger. So what we have to do here is we need to initialize our birds. Now, a bird is itself just an entity. And as an entity, it has its location. So it's going to have a bird Y location, which is going to determine where it is on the screen in the Y direction. And we're going to select this as a random starting approach. Now, sometimes you want your agents to have a consistent starting point, but to kind of prevent the agent from brute forcing its way from learning its position, we're going to randomly position this agent somewhere along the Y-axis on the screen. This lets us do an interesting thing where agents can't kind of learn from their starting position. They need to be able to adapt their position right from the start. The second thing here is the bird X location. This is just its X location on the screen, and in this game, this remains consistent. So we're going to keep all the agents in the same X position. The next step here is to determine if this bird is alive or not. So what we're going to do with this is track whether our bird has hit a pipe or not. And this is going to also be used to improve our agents or keep track of what the score of our specific bird is. And finally, we have our score. So this score is going to be incremented each time a game tick passes. So after about 1 second, our agents would ideally have about a score of 60. After that, we keep track of the jump status. So initially, our birds aren't going to jump immediately. They're going to wait for a few iterations, kind of get close to the pipe, and then either do a jump or not. After that, we keep track of our velocity. So we kind of have a physics simulations here. So gravity is going to affect how our bird acts. Initially, with a 0 value, it's not going to go too high, it's not going to go too low, and this value is going to change through iteration. So we're going to have our agent start at a static position and kind of slowly start going downwards due to gravity. Once it flips the jump value, it's going to go up. And again, gravity is going to slowly bring it back down. And finally, we're going to set the bird's color. Now, this is just to help us track how our agents perform in the world. We're going to set older agents to have the red color. Brand new agents are going to be yellow, and so forth and so forth. So we've kind of discussed this already. And the last segment here is the brain of the bird. The brain of the bird here is going to be a simulated artificial neural network. So we're going to assign a neural network to each one of these birds with a specific architecture. And we're going to roll back right after we define our entities into the networks itself. So the network has an architecture. And what this means is that we define how many inputs and how many hidden neurons or the hidden layer neurons does this network specifically have. So we have 4 inputs. We've already defined what the network is going to be looking for. It's going to be looking for the bird's Y position, the pipe's Y position, the bird's X position, or rather the pipe's X position, and it's going to be keeping track of the velocity. So it's going to know whether this bird is going to jump or not, or it's going to have all the information. And we're going to be leveraging this brain in order for our algorithm to self-improve. After we define 100 of these agents, we're going to start defining a handful of pipes. So the pipes are basically our obstacles, and we're just going to send them about 300 pixels apart from each other. We're going to define some kind of a pipe speed, which is going to be 2. This is shown to give us decent results so far. And we're going to add all of these entities into our entity kind of bag, which is where all the data is going to be held. The second segment here is adding all of our individual systems. So the first thing we need is our user input system. This is very quickly going to be abandoned because we're not going to be using this manually. The second system is our jump system. So once we know whether our bird should jump or not, we use the jump system to change the velocity accordingly. Then we need a physics system. And the physics system determines whether our agents are going to move up or down or so forth. Then we need a collision system. This is going to check whether our birds have collided with obstacles. Then we need a reward system. So if our bird has gone through a epoch without hitting any of the pipes, we're going to reward the score for that specific bird. Then we need an AI system. So the bird, once we determine the bird is alive or not, we're going to have that agent react to that specific input. And then we're going to render this so we can see it. Finally, we're going to have a little bit of delay here so that we can keep track of this. Let's try it at 60 FPS. And we're going to check if this simulation needs to be reset. And the way we check if the simulation needs to be reset, we're going to check if we have any agents that are still alive. If those agents are alive, we're going to carry out with another iteration of our simulation. If no agents are alive, we're going to reset the status of all of our agents and perform some of the genetic mutations we need. Finally, once we have our entities and systems, we're going to merge them together and run this game. Now, two things, or maybe actually four things that kind of strategically skipped here are the neural network that we're going to be using and the genetic algorithm we're going to be using for the optimizations. So if we go back all the way up here, I've mentioned that I've skipped talking about the neural network simply because I feel like it's a topic on to itself. Now, when people hear the term neural network, they usually think of something that's horribly complex. But here, there's an example of a neural network in something like 50 lines of code. I think there's maybe less than 20 lines of code. We realistically only need about 3 things to have a neural network. We need to have some kind of way for keeping track of an array of numbers. We need a way of doing multiplication somewhat efficiently. We need a way of calculating a output. This is where the sigmoid function comes in. And then we just need to interconnect those values. So in our case here, our class for the neural network does a handful of things. Firstly, it's going to determine what the input size of our network is going to be. This is how many points of data our network is going to see. And depending on the problem, we might have more inputs or not. The second parameter here is the size of the hidden network, or rather the number of neurons in the hidden layer. So this is just a multi-layer perceptron. It looks at some data in the front of the network or the input side. It processes it in a hidden layer, and then it provides an output. But we do need to define this architecture. So in our case, we define the number of inputs, we define the number of hidden nodes in the hidden layer, and we define the output size. Now, this requires a little bit of domain experience to kind of get right, but by looking at the simulation that we're going to be doing today, we can kind of determine what kind of a task it is. So in machine learning and artificial intelligence, there are only really 2 types of problems. And on a technicality, dare I say, there is only really one kind of problem, but let's not get ahead of ourselves. Any machine learning or AI algorithm can only do one of 2 things, or rather one thing, and that's predict. Based on a set of inputs, our algorithm can only predict one or multiple things depending on the architecture, but can only predict what is based on the input information. And this is excellent for carrying 2 types of problems: regression problems and classification problems. Regression problems involve our algorithm looking at a few values and giving us a continuous value as an output. So, for instance, if you look at my height for the last 5 years, you can kind of fairly accurately predict what it's going to be in the next year. This would be a simple regression problem because it can be any value from 50 to 100. And the second, let's say, popular problem is classification. So you would look at some of the characteristics of a specific entity, and then you would classify whether it belongs to one group or another. If you look at, for instance, a basketball, you could look at its color, you can look at its shape, you can look at its texture, and then you can classify what sport it belongs to. So if you look at a football, you're going to say, okay, the ball is round, it's black and white, it's going to be a ball for soccer. If you look at an American football, it's kind of an egg shape, it's brown, you're going to say, okay, that's specific value. However, classification can be looked at as a special case of regression. So our algorithm is actually going to predict a probability of a specific value or a specific entity belonging to a specific class, and then we're going to define a cutoff threshold where it belongs to one class or another. Fairly abstract, but the way we look at our problem here is we're going to show our bird where it is on the screen. We're going to show it where the next or rather the upcoming pipe is on the screen. We're going to tell its velocity, and then we're going to ask the network to classify whether this bird should jump or if it should not jump. It's a fairly straightforward look at this. Look at the screen and determine whether you're going to jump. This is what humans do. This is what this neural network is going to attempt to do. So once we initialize our network, we need to provide it with an input size, the number of hidden layers, and finally an output size. We're going to set our weights to a set of number of random values based on the input size and the hidden size. So input weights sit between our input layer and our hidden layer. And our network is going to have a multitude of weights depending on the specific architecture. The more layers we have on the input and the more layers we have on the hidden layer or the output layer, the more weights we're going to have. And we don't want to have too much weights. If we have too many weights, our network can go into overtraining. So it can learn from the data and can adjust itself to give us what we expect rather than what can be done. The second step here, we need a set of biases. Now, biases are used within a neural network to avoid networks kind of locking up. What can happen here is that you can have an input value that's close to 0 multiplied by all the weights, and then that won't contribute to the network. That won't be able to run through the aggregation function. And the way we kind of adjust for this is we introduce biases. This kind of moves our activation functions to the left or to the right, so that these values, even though they're 0, will contribute to the classification. Now, in our case, we're not going to rely too much on biases. This is going to give us a slightly worse performing network, but weights themselves can most carry our classification here. The second part is our activation function. Now we're going to be using the sigmoid function. This isn't a particularly powerful function, but what it allows us to do is convert our values of inputs to a value between 1 and 0. This is a fairly efficient way of determining how our weights would go. So if, for instance, we had 4 or 5 input weights, when we sum them up, we would get a 5 or a 10 or a 15. The sigmoid function simply lets us convert this to a specific value between 0 and 1. This keeps our computations low. We don't have to keep up with a lot of values. And we also get to maintain a lot of the data. So we're not going to be dealing with negative values, and a lot of the mathematics is kind of smoothed out here. Finally, as far as this goes, we're going to look at what the feed-forward function in a network does. We will come back to get genome and set genome, but for now, let's look at what the feed-forward function does. So the feed-forward function does is it takes some inputs and it feeds them or multiplies them by the weights, stores them in the hidden layer, and then from the hidden layer, multiplies the weights by another layer of weights, and then we get our output. Fairly simple. This is how all neural networks everywhere work, with a handful of exceptions, but it's going to provide some kind of an output. Now, this output can be either positive or negative and can be any value between -1 to 1. This isn't great for a classification. We want to have a true or false value. And the way I've defined this cutoff point for our network here is simply whether this value is larger or smaller than 1. So our network is going to start with its optimization. If the value goes above 1, we're going to have the bird jump. If it goes below 1, the bird is going to ignore the inputs and it's not going to take any kind of an action. So that's the most basic neural network. Like I've said, I'm pretty sure this can be implemented in less than 20 lines of code, and some of the lines here can themselves be removed. The next two bring us to our genetic algorithm. So the genetic algorithm, as we've seen, simulates some of the ideas from evolution and from nature. So each individual, when we look at nature and everywhere else, more successful individuals tend to have more offspring. And this is mirrored by the population having more successful individuals in the next subsequent generation. So if you look at, for instance, how humans have tamed dogs, we would find a wolf. We would find a wolf that's friendly towards humans, and the offspring of that wolf have a high chance of also being friendly to humans. You repeat this over 100,000 years, selecting for those that are more friendly or those that are more aggressive, and you get different breeds that specialize for different things. This is what we're going to be doing in our simulation. We're going to be simulating birds, and we're going to be selecting for birds that are very good at dodging pipes. However, we do need to, and we're also going to be borrowing through two other systems from genetics. We're going to be borrowing mutation, and we're going to be modifying the crossover system that's used to create obstacles. So the first thing we need to do here is figure out how we're going to encode our network. The first thing, we need to get our genome. So in our case, we're going to be using our weights as a genetic marker. We're going to look at all the values of all of our weights. We're going to encode them as a single array, and each one of these weights is going to become a genome onto itself. So some weights in the first layer 1, 2, and 3, we're going to flatten them inside of our array, and we're going to use those as genetic markers. Finally, what we also need to be able to do is set genomes. So once a network gets a new genome, we want to be able to store that genome inside of our weights ourselves. So what we can see here is we reshape our genome into a specific input and hidden layer size and set those values as our new genome. This lets us carry over traits from previous well-performing individuals. Now, a little bit more of a note on the mutation algorithm here. So what we want to be able to do here is two things. So the way things evolve usually is through mutation. So occasionally mutations happen. These are random alterations to a genome. And these happens due to exposure to elements, environments, and so forth. Every once in a while, an agent or an individual will slightly alter its genetic code if given the opportunity. And this usually manifests as a change in either the structure or the behavior. In our case, we have our mutation algorithm here that realistically only needs the top part of this. So our mutation algorithm here is going to take a genome, it's going to run through that genome step by step, and it's going to occasionally randomly encode a value. So one of these values is based on the rate that we provided here, is going to get changed to a random value. So it's going to run through all the weights we have, and it's going to set it between -1 and 1. This lets us have a fairly consistent, let's say, behavior in our network. The second segment is our crossover gene. So we've talked about how recombinations are performed when, let's say, we create new agents based on existing agents, and we're going to do that by taking two genomes. So we're going to select two random individuals from a population. Now, these aren't going to be entirely random. We're going to select individuals that have traits we enjoy, and we're going to run them through a crossover operation. What this does is it takes genes from one agent and genes from the second agent and kind of switches them up a bit. So it's going to run through each genomes, and based on the random value that's determined by the rate, it's going to kind of swap these genes around. And this creates a new agent, which will hopefully inherit some of the characteristics of their parents. And of course, we will see this in practice. So these are the two artificial intelligence segments of our agent. This lets our agent firstly look at the environment and then react to that environment in the shape of a network. And then secondly, the mutation algorithm here, or rather the genetic algorithm here, lets us change how an agent thinks through each subsequent generation that we're going to be working with. To make this work, we need two additional systems. We need an AI system, and we need our reset system. Now, the reset system, admittedly, here could have been done a little bit differently. It could have been split into two systems, with a mutation system or an evolution system and a reset system as a separate segment, but a slightly longer function is in the end of the world in our example here. So what is our AI system going to do? Well, what we are going to be doing here is we're going to be feeding our agents information about our environment. So each one of the agents we have is going to look at a system, it's going to get about inputs. Those inputs are going to be processed through the little simulated brain that we've built, and then they're going to either perform an action or not perform an action. In our case, they're either going to jump or they're not going to jump. So we've kind of followed some of the functional principles here, and we're going to create a new set of entities. For each one of the entities, we're going to look at if they have a brain in them. So we're going to check if they are a bird or if they are a pipe. If they are a bird, we're going to have to do a little bit of a trick here. So since we don't really have an idea of what the closest pipe is, we only know what the location of all the pipes is, we're going to set a minimum value of distance from any pipe at all to 1,000, and we're going to see which we have on our screen is the closest to our bird. Why is this? Well, we need information on this so the bird can time its jump. So we're going to get information on that specific pipe. We're going to see whether that pipe is close to the bird, if it's a subsequent pipe or a pipe that the bird has passed. If it's a pipe the bird has passed, we don't really care about it anymore. We only care about upcoming pipes. And then we're going to see whether that pipe is the closest one. Once we determine what the closest pipe is, we're going to store that. And the second part of this is just using the brain to feed forward through the neural network. We're going to provide the bird's y coordinate, so where the bird is on the screen, as far as the y coordinate goes. We're going to get our velocity of the specific bird, which is going to vary depending on how recently the bird has jumped or not. And then we're going to provide this with the two stored values. Now, these stored values that we've created here are going to be the pipes x component here and the pipes y component. Another thing you might notice here are these kind of rogue equations that are placed in here. So if you've looked at the very basic implementation of the neural network I have here, there is no normalization. So whatever comes into the network, it just feeds through the network the way it is. This is problematic since different values can have different influences on the network. So if we have a value that's varying between 0 and 100, and a value that varies from 0 to 1, they're not going to have the same influence on the specific decisions of the algorithm. So if we look at something that's well addressed by AI, for instance, with kidney disease, blood pressure is going to vary a lot more than number of cups of water a day. However, each one of these parameters has an equal, or rather has to have an opportunity to have an equal contribution to our network. So what we do here is we divide the position of the bird with the maximum width of the screen and the maximum height of the screen. And this converts this one specific value to a value between 1 and 0. This normalizes our data on the input to the network, allowing each one of the features we're providing to the network to contribute equally to the decision. So in this case, location in X isn't going to contribute any more than a pipe location Y. The same goes for the bird's Y position. We're going to divide it by 400 simply so we have a value that's between these two values. And once we have our feed-forward network fed all the information, it's going to do all the computation and the background, and it's going to provide us with a jump component. That jump component is going to be stored for later processing in the jump specific system that we've looked at above here. The second system, or rather the final system we're going to be looking at for today, is the reset system. This has a very simple kind of role. Firstly, it resets the environment to the starting point if there are no agents in our populations left alive. So there is a new group of entities. Each one of these entities is going to be appended once an agent is determined if there are still, let's say, agents inside of our world. The next step here is we need to check if there are any living agents left. If there are no living agents left, we're going to do a reset. So once we have decided to do our reset, we need to do quite a few things. So this Z is here just for some kind of specific offset, but once we determine that there is no agent inside of our population, we need to do a few things. Now we need to look at our agents and evaluate them. Have these agents performed well in our system or performed poorly in our system? If they performed poorly, what is the result? If they performed well, what is the result? This is where an objective function comes in handy. So in our case, we have kept score of each of the birds and how far they've made it into the game. So those that have made it deeper into the game have a higher score. Those that have hit the pipe very early on have a much lower score. And we're going to use this as an objective function. So objective functions in an AI way tell us how well an algorithm performs. If we're looking at the classification algorithm, we're going to be looking at their classification accuracy, their precision, their F1 score, recall, index of alignment. There's a lot of metrics we can look at this. But since we don't have an objective value that is a ground truth in this case, we need to kind of improvise. We need to build our own objective function that determines the quality of our agent inside of the environment. If we go back to our practical example, when having a dog fetch, we would, for instance, keep track of the number of times a dog would properly fetch the stick for us, and we could evaluate and rank dogs on their performance based on this. However, this becomes very difficult when you have not so easily defined tasks. So parking a car, how do you know if a car is parked well or not? Well, one objective metric is if you've had hit another vehicle while doing so or not. But if you've hit another vehicle, your score is going to be 0. The other segment is how well it's aligned with other vehicles and so forth. So this is where reinforcement learning kind of comes in handy. In this case, we want our agent to stay alive as long as possible. In some other case, we might want to have our agents live for a shorter period of time. So until a vehicle is fully parked, we're going to not reward our agent. So we're going to sort them differently. Now, when we have our agents evaluated based on their score, we want to sort them. We want to be able to select the best of the specific population. So we're going to run through all the birds and we're going to sort them based on their score. And this is where we run into a kind of point of hyperparameter and hyperparameter tuning. So we've already mentioned one group of hyperparameters inside of an artificial neural network. This is our architecture parameters. How quickly or how many neurons our networks are going to have and how well it's going to adapt to a specific problem is largely dependent on the amount of neurons it has inside of it. And in our case, we've selected the generic version that I know is given okay result for this. We're going to be using 4 inputs and 32 hidden layers. The other parameters we're looking here are parameters for the agent mutation. So let's see how much of our old population is kept. In our case, we're going to say 25%. Then we need to determine how much of that population is going to be children. So let's say we have 25% of our agents remain from the previous population. In the next step, we're going to use another 25% to be representation of children of those best performing agents. Then we also want to create mutants of that population. So we're going to run through another set of the best performing agents, and we're going to mutate each individual genome for these agents. And finally, to make sure that occasionally random things do happen well, we're going to add 25% of new agents. This introduces new individuals into our population and keeps our network from stagnating. What can happen inside of the genetic algorithm, and what does often happen, is that our population stagnates. It finds a good enough optima and then just never leaves it. This is why we introduce new agents that might be better at a specific task, might be worse at a specific task, but through mutation and crossover, this will let us kind of explore new combinations that haven't been seen so far. Well, once we have all of these agents selected, I've kind of separated them into 3 arrays here so I can color them differently. We want to do a few things. So we want to run through each one of these agents, and we just want to create them, or rather store their neural networks in something I call a brain jar. What we do is for each one of these networks we have here, we're going to take their genome and we're going to store those genomes into one giant group of neural networks that we can use to recombine our birds. After that, we reset our birds and we basically set their Y location in a random value between 100 and 300. We set their status to live, so we bring them back into our simulation. We reset their score, which is very important here because we don't want our agents to kind of linger on to generations. We reset their function or their jump function. We set their velocity to 0, and then we assign a new agent a neural network from our stored values here. And this is what lets agents kind of retain some of their memories. The best agents maintain the best neural networks. The worst agents get some of the newly generated neural networks. And our little final step here is we have set a color for each of the agents. So the first 25% of the agents are going to be colored red. These are going to be our senior agents, those that have proven themselves to work well. After that, we're going to increment our agent counter, and we're going to see the next group of agents. These agents are going to be colored, I think, green. These represent the children of the best agents. Then after that, we're going to introduce our mutated agents. These are going to be blue. And finally, we have our fresh new agents, which are going to be yellow. After we reset all those agents, we just reset our pipes as well. And then we run through our simulation. So now that we've kind of talked through all of this theory, let's see this at work and discuss how our agents improve. So every time we start this simulation, we can see we have a group of agents. Let me just slow this down so we can see it run in order to discuss this at a much slower pace. Currently, it's a little too quick. Just say 5 frames per second. So we start our simulations with fresh agents. All of these agents are new. They don't know what their environment is. And as we can see, a lot of the agents just decide to jump or not to jump. And these acquire fairly poor scores. They're fairly quickly removed from the population. But every once in a while, one of these agents gets a bit of an idea. It goes like, well, we've seen this environment. Let's see what we can do. In the first few generations, there's no real chance of having good agents perform here. It's all based on randomness. However, after a few kind of chances and coincidences, we will get an agent that knows it's supposed to jump through this group. So I think we're having the first agent here successfully jump through our group. That's going to be, yeah, we have one made it through the first pipe. you're already on the first generation. And this is going to be our best performing agent in the next one. This agent is going to have the highest chance of having offspring, and it's also going to remain in the next generation. And as we can see, we have a veteran agent here, this one colored red. That's our leftover from the previous agent. And we can see that maybe it didn't perform so well, but the blue and the green agents here do perform well. I'm assuming that the blue one is a mutant from the previous generation, but this new agent is also performing well. So it's going to have a high chance of having offspring in our simulation. Another thing I can mention here is that we only really need 3 pipes, despite this system generating a seemingly infinite amount of pipes. Once a pipe makes it all the way to the left, it is teleported to the right with a randomized location. So we have our agents slowly running through our simulations, and we've seen new and fresh agents be generated. In the next iteration, they become veteran agents. Those are agents that have kind of shown to have a talent for navigating this problem. And we can see there's a veteran agent that almost made it here, not quite perfect. So one advantage of building your own gym is you can very much tune it for what you need it for. So in our case, we can see that simulation runs a little bit too slow for us. We can speed it up to 60 frames per second, and we can see this run in somewhat closer to real. We have a very good agent early on. So we already have some agents kind of improving and producing new generations that show excellent results. Our veteran agents are slowly going to accumulate in our population. So this is clearly a very lucky individual. But eventually, this is going to start running towards agent children having better outcomes. So here we have 3 agents that are good. Now we have 5. One was kind of 4. There we go. So through simulations, we're going to see more and more agent children performing well in these simulations. And eventually, with enough simulations, we will run towards a faster convergence. Oh, there we go. We have a offspring performing significantly better. So this will slowly run through each one of these simulations, one by one, and our population will slowly improve. And once we get an agent that can beat enough of these pipes, we can say that our training here is mostly complete. We can repeat this for any kind of simulation, and the entity component system is once again very flexible. So in this case, we've used a very simple simulation. Again, kind of a 2-hour talk isn't enough to carry out something more complex, but even with very few lines of code, we can already see how reinforcement learning works. So we have our agents in the population that are kind of brute forcing their way through our simulation. In each simulation, we are selecting for better and better individuals. These individuals remain in the population, and they have a higher chance of having more and more children. Through each subsequent iterations, we're going to see, again, it depends on the number of iterations that we're going to do, but we're going to get more and more better agents in our population. And hopefully, eventually, we're just going to see children agents perform incredibly well. So this is fairly slow. So let's run it at 300 frames per second and see what we can do with this in real time. And while this kind of runs in the background, I can take some time to answer Q&A if there are any questions and thoughts. Otherwise, I'll just be giving commentary towards how this algorithm can be improved. So initially, the way I wrote the neural network, it could only really encode positive and negative value, or rather positive value. You can only have one as an output, and this would require me to tune the output value of the network. So we would have to kind of select when a jump would happen based on experience. What I've since then done is I've kind of converted the network to be able to work with positive and negative values. Negative values for jump tell us that the bird isn't supposed to. Oh, thank you very much. I'll make sure and update the last segment of the code with the place here. It could be that an older generation of the implementation is here. Like I've said, the code went through a few iterations here, and I'm not the best at simulation management. There's also another interesting simulation with the genetic algorithm, for instance, for tracking passwords, where the algorithm kind of slowly learns towards a solution by trying different calculations. So this might be interesting as for CS students. Again, the genetic algorithm is a very popular metaheuristic algorithm and has shown great responses in again, like I said, I will be uploading the complete version as well, just so everybody can use it. And in the case that you do use the code, let me know. I'm really interested in what other students are going to build with this. I myself have spent quite a bit of time trying to get this to work the way I want it to. So I'm always excited to see changes and alterations of the code and what interesting kind of topics they're built with this. So if any other questions show up, I will be answering as I can. So the way the kind of optimization works here is not directly how Q-learning works. We're not going to be using backpropagation. Backpropagation works great when you have true positive values. So if I knew exactly when the bird was supposed to jump, this would be great for backpropagation. I would say, okay, this was the expected value that you were supposed to get at this point. Correct the weights. I don't exactly have that in this simulation. And the more complex simulations get, the less and less labeled data exists. If you want to look at how backpropagation can be used in the context of this, maybe something like behavioral cloning might be more interesting. But the way we use it here is that we maintain the weights and biases of networks that are performing well, and then we're keeping those as, let's say, good traits for birds, and then discarding the agents that are performing poorly. It does require a little bit of, or rather, we're only keeping the weights. We are kind of discarding the biases here as, well, even with the weights, they are performing significantly better at the game than I am. But we're discarding the weights and biases of networks that aren't performing well, and then we're importing these. So we're importing these through pure mutation. Now, Q-learning and backpropagation work on a slightly different mechanism. Q-learning uses policies. So an agent would be given a policy on when to jump. Once that policy is met, we would remove training. Since we only have a very simple problem here, there isn't a lot of ways to break it down into simpler components and then apply Q-learning. And again, Q-learning requires a little bit more coding than this example. So I've kind of tried to keep it concise within one presentation so that we can go through all the code rather than focus on a very small segment of Q-learning. It would kind of require a few sessions back to that. Any other questions? Please go ahead. Another kind of interesting observation with this algorithm is that it lets us look at the convergence of each one of these examples. So an important thing when looking at optimizers is how fast our algorithm converges. So in any search space, there are a few local optimas and a few global, or really only one global optima. The global optima is the one true best solution. And this really depends on the major advantage here, there isn't really an advantage of using the genetic algorithm over Q-learning for this kind of an example, except for the fact that it's very much quicker to code and easier to understand. So when addressing a much more complex problem, I would myself go for Q-learning, but Q-learning kind of goes out of the scope of a simple demonstration. We will still get good results with Q-learning, but this is a lot more visual to understand. So if we were to have a lot more time, maybe a workshop that lasts a day, I would make sure to kind of go through Q-learning, but the genetic algorithm can run on a relatively cheap and affordable CPU as opposed to Q-learning that requires a little bit of more computational power. So one advantage is, again, the simplicity of the algorithm. It's basically combine what you have until you get something that works, as opposed to kind of aggressively run through each simulation, implement policies, and then train from there. While the genetic algorithm, like I said, is fairly computationally simple, although it does require a little bit more trial and error to run through the simulation. So another kind of important thing while I'm still talking about the genetic algorithm here is the convergence rate of each one of these algorithms. So if this algorithm, for instance, now it's struggling to find a way of tackling large shifts in the pipe. So if we can see an example here, when the changes between the values of this gap are small, the algorithm can kind of adjust to it. When the change is large, the algorithm usually hits one of the lower or the higher pipes. This is mostly due to the premature convergence of the genetic algorithm. So the way I've tuned the remaining objects or the remaining generation here, it much more favors algorithms that will just adjust to where the pipes are a little bit and then work just well enough. It leads to a premature convergence towards a local optima. So this local optima doesn't really let it fully kind of explore the search space and find the true global optima of weights, which will let it beat this simulation very quickly. So this would require a little bit of hyperparameter tuning and working around. So I encourage everybody to cast the code. Once again, I will be uploading the full version by the end of the talk. We're going to, I encourage you to try with a few other hyperparameters. So in my experience, the genetic algorithm for, let's say, beginners is the simplest version of it. But there's a lot of algorithms from the metaheuristic branch that are very interesting. So that's something I very closely have been working with for the last few days. Something like the sine cosine algorithm is very powerful and very popular. Things such as the reptile search algorithm leverage a few other samples. Once you kind of understand the core concept behind the metaheuristic, it becomes a interesting topic to work with. So genetic or other metaheuristic algorithms leverage three mechanisms. Firstly, they manage they are capable of addressing NP-hard problems in realistic time. So those of you that have kind of run through computer science a lot have encountered problems that are hard. This means that there is no real discrete way of mathematically creating a model that can be solved within realistic time. So for instance, if you were to crack a one-time pad, it would take infinite amount of time to kind of determine the best solution. So oftentimes a good enough solution is just as good or rather better. If you're determining the distance between two locations, such as Belgrade and Novi Sad, you have infinite paths that you can take, but only one is true optimum. So what you can do here is you can run through all the computations in the world to determine this distance, or you can run through a handful and then find a best solution from those. Now, this solution might not be the best truly, and you can't really mathematically prove that it's the best, but it's close enough that it's an acceptable solution. So this is one way of one very well-known problem inside of, let's say, computer science and optimization. We want to have our algorithm be able to, oh, we have a good agent here. That's interesting. I'm sorry, I very easily get distracted by these simulations always. One kind of advantage of this is that we can handle complex problems in real time, and researchers have tackled many complex problems in real time. If we look at a, let's say, architecture of a neural network, if we have 32 neurons with four input neurons, we have 4 to the power of 32 options for what our weights can be. And if we were to try each one of these with floating point values, we essentially have an infinite search space. So going through all of the simulations that we can, eventually, firstly, most of these are going to yield poor performing agents. Secondly, eventually we're going to run out of computational power. So even the best supercomputer can't run all the simulations possible. So having something like a metaheuristic kind of guide our simulation towards a better solution lets us leverage reasonable computational power for this. So some kind of suggestions for this are the artificial bee colony algorithm, the ant algorithm, the sine cosine algorithm, and maybe the firefly algorithm. These are kind of good, and they have some advantages and disadvantages over each other. So for instance, the genetic algorithm is fairly easy to implement, but the firefly algorithm, for instance, has a much better exploitation mechanism. So it will focus on solutions a lot quicker, which gives it the advantage when computational power is limited. The genetic algorithm, like I've said, it's fairly simple and it gives decent results. It's fairly flexible and easy to implement. So I encourage everybody to, given the chance, try the simulations themselves and kind of remove the stigma of AI being hard. It's very applicable. We can also use a larger architecture. So in my case, we only have a simple multi-layer perceptron, but using something like recurrent layers will let the birds remember subsequent interactions and kind of improve on that. No, of course, like there's a lot of papers on deep learning and genetic algorithms. Some of the, let's say, issues with this are the rate of convergence. So we, in this specific sample, have an algorithm that converges too quickly. We can see that currently this simulation is running into problems as far as finding the true optimal solution. mostly because it's favoring quick solutions over more complex examples much more quickly. So this kind of leads to premature convergence in our simulation. As far as tabular data, it might be a little bit difficult. I suggest for tabular data, mostly using the artificial network for it, and then optimizing it through the genetic algorithm. So what you could do is you can put one of the tabs that you have as a target for your network, and then run the network through your data and see how far off it is. And then you can use the genetic algorithm to optimize the architecture of your network. And a lot of work has been done in the field, focusing specifically on these challenges as well. So in our case here in the simulation, we've looked at how the network works. We can take a look after this. So once the training is over, essentially in this case, there is no over criteria. What I would do is I would define a criteria of maybe and the algorithm passing through 100 pipes, and then I would store the weights of the network as a list that I can then input to another list and then use it, for instance, to simulate a game or anything else. So the idea behind it is that the genome we've used to mutate here can be used to store the network information as well. So we can combine it with any other example as well. As far as e-commerce, once again, can be kind of used here is I would primarily use the artificial neural network for that. I would use it as a set of inputs and then as a set of outputs. So for instance, if you were looking at potential clientele for a specific product, I would look at clientele that have bought that same product before. And I would look at parameters that contribute towards them being interested. So maybe their browsing habits, maybe their age, gender, any other topic that might contribute to their interest in a specific problem. I would then run an artificial neural network towards it and then determine whether the classifications are correct or incorrect. Then I would run a few algorithms on it. I would run a few neural networks on it, and then I would select the algorithms that are closer to the solution. Eventually, it will give us a, let's say, solution. So tabular data can be treated the same way as pipe data is treated in this specific example. Any other questions? So after kind of looking at the examples here, there's a few other things that can be a stepping stone from this point. One would be kind of improving on the premature convergence of the algorithm. Oh, yeah. What we can do here is we can save the entire population. So with just 2 lines of code here, if I wanted to do it. So let me just terminate the simulation and we can see what we can do. Once we have our best agents here, we can simply use this best tab here and say the best pickle and just provide a name. And every time our simulation runs through this, it will save the best performing agents in a specific pickle. So an interesting way of doing this is to kind of keep track of the generational data. So we could run our simulation. We can run our simulation continuously if we use, for instance, something that can allow us to run this a little bit faster, just to see what the outcomes are going to be. We can keep saving the best agents from each population indefinitely until we get an agent we're kind of happy with. So it also allows us to continue training. I didn't implement a way for saving the models, kind of anticipating that we wouldn't have as much time, but we can also keep saving the best population for each subsequent layer. Once we have a method for saving the genome, we can just re-import that genome in the next example as well. So we can have these learn in one environment and then, for instance, learn in another environment. This allows us to build several gyms. For instance, we can build one gym that teaches the birds to jump through hoops, and then we can use that example to fit this algorithm to something more complex, where, for instance, these hoops themselves move. So there's quite a bit of potential in future works here, especially focusing on changing the simulation here specifically. So this, again, example, fairly simple, mostly due to time constraints so that we can code everything up and kind of go through all the concepts. But you can, of course, alter the code as you see fit. It should be fairly simple. Change the systems, change the entities, and you can have an entirely different simulation. So if you want to play Atari's Breakout, you would just run a simulation of Atari's Breakout, change the simulation function, and that would be most of this, let's say, adapted to another example. Any other questions? All right, I'm very glad we've got to run through the entire example. Again, thanks for everybody for being here. I'm open to all the feedback. I'm pretty sure that I provided an email as well, so we can stay in touch if you're interested in altering this or building on this further. I will make sure to upload or rather we will upload to the same drive the updated code for this simulation as well, so that you have a complete example. If you build on this, please let me know. I'm really interested in what others are interested in implementing here. So always an interesting topic, always an amazing audience. Thank you once again for being here, and thank you. I think tech support might still be muted.
Oh, okay. Can you hear me now?
Yes, thank you very much.
Okay, thank you, Luka, for this tutorial. It was really interesting, and I enjoyed it myself too, and I hope all of the attendees did as well. Thank you all for listening, and yeah, bye.
Thank you as well. Bye.